Let's start our sessions. I want to welcome all of you, both presenting authors and also people who will attend this webinar or now or registered later on. My name is Giuseppe Quaglia, and I am one of the organizers of this workshop that is entitled Field and Service Robotics Toward Deployment in Highly Challenging Environment. Organizers are Giulio Reina, Marco Carricato, Edoardo Ida, and Dario Guastella. I want to thanks to RIM community that organized this wonderful conference, and also the opportunity to have this workshop that are very interesting and effective. I want to spend a few words about the organizing committee, because we are part of automation and robotics team in the applied mechanic group in Italy. You know that we are organized as a scientific group in many different groups, and we are working for this scientific group. But since this is an interdisciplinary topic, you will see both presenting author and also participant who will be part of other discipline, because you know robotics is a very wide field, and it is needed to have a network of researchers that work together. So this is also a symbol for us. We divided the morning in two parts, one more devoted to agriculture, and the second devoted to highly challenging environment. I want to leave the floor to my co-chair, Giulio Reina, Marco Carricato, to have a few words of introduction of themselves.
So, yes, thank you, Giuseppe. And let me thank again the audience and the speakers for joining us this Saturday morning. So sorry for that. We have a really exciting program this morning, however, that covers the latest efforts in the deployment of robots in real context to accomplish highly challenging tasks. Well, so this witnesses the current transition from traditional fixed-base robots used within structured industrial sites to the outside world, that in our view represent the current challenge for the net of robotics, one of the main challenges for the next decade. So the adoption of field robotics has rapidly increased, with many notable examples that have been proposed and demonstrated for operations in overground, underground, and underwater settings, without forgetting the success of planetary exploration performed by unmanned rovers. Well, according to the International Federation of Robotics, the market projection suggests that in a 10-year time, the number of service robots sold per year will exceed the number of traditional fixed-base robots. So this workshop will picture the current state of field robotics in Italy. We will have also a contribution from the Kyushu Institute of Technology, Japan, that I especially thank. Again, I would like to underline that we have presentations covering the whole long Italian boot, so from north to south, with the real multidisciplinary and broad perspective, with contribution coming from different areas of engineering, but also from agricultural sciences, from universities, but also from the National Research Council. So we really looking forward to the presentations. So I would like to pass the ball now to Marco, and so we can then start the workshop.
Good morning, everyone. A welcome from my side as well. I'm Marco Caricato from the University of Bologna. Much has already been said by my colleagues, so I will just to try to be very short. As you perhaps noticed in our schedule today, we have two sessions. The first session will be mainly devoted to robotic for agriculture. We will have 5 papers with an overview for service robotics for agriculture, paper concerning agroforestry robotics for alpine environments, technology for digital and sustainable agriculture, and comparing finite element method and experimental data to predict rolling resistance in grape transporting vehicles, and also cooperation of unmanned system for agricultural applications. The second session instead will be devoted to unconventional robotic system for highly challenging environment besides agricultural purposes. So we'll have many, well, and 5 presentation as well, mainly devoted to mobile robots. We will have one presentation devoted to hybrid locomotion systems for mobile robots, then a presentation devoted to mobile robots for service applications, another presentation devoted to mobile robotics for infrastructure monitoring, presentation focused on navigation tools based on learning methods. And finally, we have a presentation for unconventional robotic systems driven by cables replacing cranes in challenging environments. So basically, this is just a very brief overview of what you will listen from us, well, from our speakers. And I remind everyone that each slot covers 14 minutes. 12 minutes are for speaking, 2 minutes are for questions. At the 10th minutes, the chair of the session will just show himself on the video, and this will be a sign for the speaker that he has only 2 minutes left. So enjoy this very exciting workshop and have fun. I think that actually I chair the first part of the first session that may start right now. Actually, we are exactly on time. The first presentation will be, so this session, as I said, will be devoted to robotics for agriculture. And the first presentation will be about service robotics for agriculture and overview. The authors are Giuseppe Quaglia, Andrea Botta, Paride Cavallone, and Luca Carbonari, and the presenter will be Giuseppe Quaglia. Please, Giuseppe, the floor is yours.
Thanks, Marco. Let's start for this overview that I will try to give you. And I want to thank to my group that we call with the name Saromedises, and all the group is working on these topics. And I would like to start giving a wider view of research and technology, because since we are talking about robotics, robotics is a part of technology, and the point is technology can give some answer to the strong request of sustainability that is coming every day stronger and stronger. And the sustainability is represented by sustainable development goals that bring a deeper view of our future. For example, robotics in agriculture for sure can contribute in responsible and consumption and production, or clean water, or also zero anger or good health and well-being. So these goals are reached by technological evolution. I will give some example, and the point that I wanted to underline is that service robotics can give an end to our world, to have a better world, more sustainable, more clean. And remember that we are in a system that is closed. So if we use the energy and the natural resources in a proper way, we will have a better future. Where we are talking about robotics, Giulio presented some forecast and talking about service robot. That is the second hand of robotics, because we have industrial robot and service robot. All those solutions are growing very, very quickly. You know that normally there are two types of service robot that are normally called professional service robot or service robot for domestic and household tasks. The second one is the robot that is cleaning your house or that cut your grass in the garden. But professional service robot is growing very, very fast. Obviously, the size of the market is completely different, but also the value of the solution is completely different. The continuous year growing that are forecast is around 30%. That is impressive. Where are the professional service robots used? Mainly, they are in logistics and inspection. So those are very, very important area that are growing according to International Federation of Robotics. But talking about agriculture, we are in this last part that is smaller. So that means that we are in a market that is burning very fast, but it is still starting. My opinion is that field robotics will follow logistic robotics in very short time. And my point is to present some solution from the research environment or from the industrial prototype that are now available. Starting from some category, I divided it in small size, medium size, and big size. Small size means that we have a robot between 10 to 100 kilos, very limited power. And these robots can work under the crops, as you can see on the upper image, or over the crops. They are devoted to data collection, that is tools for predictive approach to agriculture rather than reactive. So you have to predict and decide before things will happen. For example, infection will destroy your culture. But also they are devoted to weeding and hoeing. And for example, this small video gives some idea about this small size. Here you can see seeding and then hoeing. Those are the most important activity. Moving to medium size, we have tools and robots that can move in a farm. They are designed for multiple implement, multi-purpose. In this case, for example, the steer tractor, they have a hybrid motorization in order to work 24 hours a day. They are connected in order to be very accurate in positioning, and they must be safe. For example, you can see that this solution works in tree crops, market gardening, or viticulture, both with narrow rows or wide rows. again, a few seconds of images to have a look on what happened in the field. So the last part of my categories is related to big sites. What I want to underscore is that now we are mainly in a concept, so there are no products that are available in the market, but many big companies are working for solutions that will make autonomous also big size robots that are devoted to operations that require high power, so plowing, harrowing, weeding. They have to be compatible with the traditional agricultural machinery implements. And to give an idea, again, a small video, this is very interesting solution that substitute the wheels with tracks. So we finally it is very compact, highly maneuverable, and also the power that is available is very high. So it is a challenge to have a product like this. Now I want to move to research prototype, and I want to show our research on a mobile robot devoted to precision agriculture. And the precision agriculture is a crop management technique that employs tools and technologies to increase the climatic and environmental sustainability of agriculture and to increase efficiency and quality. The rover that you are looking at in the image is devoted to mapping, monitoring, and cooperation with drones. I will give you some detail, but I want to underscore also the project requirements. Project requirements that are related to vineyard activity. So the vineyard have a specific geometry, so the height of the filler are between 0.5 to 2.5. The distance is 1.5 and 2. So we have, for example, hill landscape have and also a slope that very strong. We want to build a robot with a high mechanical requirement, sustainable. So you will see that it has a limited energy consumption, high autonomy, thanks also to solar panel, the autonomy increase, and also it has sensing and a robotic arm for sample collection. This is the system. It is better to see it when it is working. So again, we choose to have a photovoltaic surface on the top, but the challenge is to move on the ground that is very complex in geometry. We choose to have a 8-wheel driven solution that is something in the middle between track and wheel, because the surface, contact surface is very wide, but at the same time we have the efficiency of wheel locomotion. You can see that that surface, the top platform, can be used for landing drones, and also we have a collaborative robotic arms installed on the platform. You can see also that we can have a wider workspace, considering also the workspace of the mobile platform. And so this is shortly our solution, and cheers for the results. So have some wine. Okay, a few seconds more. I will skip some detail. You can have a look on the passive degree of freedom that is used to steering, because we have a differential steering thanks to the speed control of the front locomotion unit. There are a passive degree of freedom according to the compensation of the unevenness between front and rear module, and this is one of the most interesting characteristics of the our mobile robot. It is able to climb the obstacle of the dimension close to the dimension of the radius of the wheel. That is impossible with only one wheel, but this wheel rocker rotation enable good load distribution on the soil and also climbing ability. Relating to the panel control, we have two orientation that can be controlled both for landing and following the trajectory of the sun in order to have a better photovoltaic effect. I'm sorry, I have to close here, and thanks for your attention.
Thank you very much. Thank you very much for this very nice presentation, a very interesting one. Do we have questions from the audience? Okay.
If there are no questions from the audience, let me just...
There is a question from here in Rome.
Okay.
Please
go ahead.
Can you hear it from
sorry,
home?
no.
Okay, I can try to repeat it.
Like, how can you be a French company that uses robots? Like, are these robots that can be used by a single partner, like economics, or something that requires a big company?
Okay, they are asking if this kind of robot can be used by single farmers, so they can be used on a low scale, or they are more for big companies that can afford them.
No, this especially this solution was designed in order to be a low-cost solution. What I mean is that we reduce as much as possible the number of actuation systems. For example, we have an 8-wheel tracked robot, but only 4 motors for traction, 2 motors for orientation of the panel, and in total we have a mass of less than 100 kilos. That means simple solution, and obviously now we are in a prototype stage, but we believe that this solution can be realized in a product that has a limited cost. Finally, it is interesting to have this type of application for relatively small farmers that want to control their production.
Okay, Giuseppe, thank you very much. I'm very sorry, our schedule is very tight, so probably we don't have the time that we would deserve in order to share opinions and comments. So the second presentation will be about cooperation of unmanned systems for agricultural applications. It's a joint effort by several institutions. The contribution is by Martina Marella, Lorenzo Comba, Alessandro Biglia, Cesare Donati, Fabrizio Dabene, Paolo Gai, and the presenter is Martina Marella. Please.
Good morning to everybody. Can you see my screen?
Perfectly, please go on.
Okay, so good morning to everybody. I'm Martina Marella from the National Research Council of Italy. And today I'm going to present some preliminary results that has been achieved in collaboration with the Università degli Studi di Torino, and in particular with the group of Professor Gai, about the cooperation of unmanned system, both aerial and ground vehicles, within the framework of agricultural application, in particular in field operations. So okay. So as we already heard in the previous presentation, several benefits can be achieved by making robots cooperative, and so thanks to the collaborative action among drones, both aerial and ground vehicles, going to optimize and coordinate the in-field operation with the guidance, navigation, and control tasks. When multiple groups of robots, fully autonomous robots, are involved in cooperative scenarios, these teams can be composed by either homogeneous or heterogeneous agents. And with respect to the task assignment strategies, we can have several different system vehicles. For example, we have the peer-to-peer solution, the architecture, the team robots, or the master slaves. The cooperative approach that we propose differentiates itself from the classical one, since it considers only full autonomous heterogeneous vehicles, so both aerial and ground vehicles, which cooperation develops on multiple subsequent phases. So not simultaneously, in order to completely optimize the mapping and in-field operation process. So our approach basically develops on 3 subsequent phases. In the first one, we have a fixed-wing fleet of UAVs that overflies the selected fields, taking aerial images thanks to a multi-spectral camera. Then these 3-point cloud maps are automatically processed and simplified into georeferenced maps that still maintain the shape of the crops, but provide us live maps that can be later used for the autonomous guidance and navigation of both ground and aerial vehicles for in-field operation, in particular spraying of biopesticide within vine rows over slope terrains. This mission scenario is placed within the project, the PRIM project entitled New Technical and Operative Solution for the Use of Drones in Agriculture 4.0, which goal is to design new tools and implements for the in-field operation performed by unmanned autonomous vehicles. And as you can see, the consortium include also other universities from the different parts of Italy. About the main actors. So in this operative scenario, we are considering a mini fixed-wing UAV. And then for the remote sensing mission phase, while we have a 4-wheel steering electric UGV developed by the Professor Guy Group for the in-field operation, and then the Q40 quadrotor developed by Market Company, again for the spring operation among the vine rows. While we have selected the Nebbiolo Vineyard in Serra do Lunga d'Alba, which has an extension of 2.5 hectares and an elevation ranging between 330 and 420 meters. So going to the detail of the multi-phase approach, the first phase is, as we said, the use of a fleet or a single, depends from the extension of the area, of a fixed-wing UAV that basically overflies over the selected vineyards in order to collect the aerial imageries for reconstructing the maps of the area. In this case, we developed a dog guidance and control algorithm to guarantee the proper autonomous navigation and guidance of these drones. In particular, we use a waypoint-based and terrain following guidance to define the optimal path. And then we ensure the robustness also to wind gust using the so-called tube-based robust mode predictive control to track the optimal trajectory. Then, once all these aerial images has been collected, we develop, in collaboration again with the Department of Agricultural Sciences, an algorithm that allows us to automate the elaboration of those images in georeferenced maps, but these maps are simplified. And to do so, we basically, first, we do a semantic interpretation of the point cloud in order to identify the different elements of the scenarios, such as the canopies and the terrain. And then we adopt a combination of a convex cell filtration and minimum Sigon area Sigon design in order to generate a light 3D mesh model of the crop, as you can see in these pictures, that can be later used for guidance and navigation of the infield drones. So how we can use these maps? So first of all, we developed an innovative filtering scheme in order to provide the diffusion of the data provided by the onboard sensors. So in terms of GPS, IMU, and ultrasonic sound, with low complexity georeferenced map in order to improve the localization within rows, in order to avoid the low accuracy of low cost components and sensors, and at the same time the not totally availability of GPS data within the bind rows. So as you can see, we have a Kalman-like filter that allow us to first fuse the data coming from the simplified maps with the ultrasonic sensors data, and then we fuse them again with the GPS and IMU data. You can see in this picture how we are able to improve the data and how we are further improving the results once more sensors are equipped on board the drones. Another way to use those maps has been to define automatically the unsupervised, using an unsupervised method, the so-called occupancy grid map, in order to identify which are the obstacles, in this case static obstacles, that are represented by the bind rows, and as well as the turning area that defines the requirements, and at the same time the constraints for planning the in-field operations of both ground and aerial vehicles. And these maps are later used for the design of the ad hoc guidance strategies for the UGV and the quadrotor. So as we said, for the in-field operation, we consider as the ground vehicle a four-wheel steering UGV. And for what concerned the guidance and control strategies, we use the classical approach based on a global path planner, that in this case is based on RT-star approach that provides us all the main waypoints along the field. And then we have the local path planner based on a dynamic window approach that provides us the feasible optimal trajectory, enforcing the non-alarming constraints of the vehicle. Once obtained the offline, the desired trajectory, we have for the UGV a cascade control strategies based on a proportional steering controller that is partially proportional in the terms of the distance and the orienting to the attitude of the vehicle, and it has non-linear features with respect to steering angles of the front and rear wheels. And then once obtained the desired steering angles for front and rear wheels, so we apply a QP as a velocity optimizer in order to obtain the optimal velocity profile for each of the four wheels. And then we go on the side of the quadrotor, in which we consider for the 2D guidance, so for the definition of the offline trajectory, the same approach that we use for the UGV, so the RT star plus the dynamic window approach. Of course, adding the waypoint related to the taking off phase and the landing phase, in which we require the quadrotor to go back to the home base at the end of the mission, while we exploit the same terrain following scheme that we use for the fixed wing UAV, in which we require the quadrotor to maintain a fixed altitude with respect to the terrain, according to the performance required by the spring operations. And also in this case, for the controls, for the tracking controller, we exploited the model predictive control scheme, again, a robust scheme in order to be able to include in the design not only the disturbances, but also the uncertainty due to the neglected non-linearities of the model, or the so-called geometrical uncertainties that can affect the control, so the tracking capabilities of the vehicle. And also in this case, you can see from the preliminary results the effectiveness of the GNC scale. More details about the work that I described to you this morning can be found in the publications reported in these slides. And from my side, it's all. So thank you for your attention. And if you have any question, I'm glad to reply to you.
Thank you very much. We have time for one question from the audience. I see Giulio. Or
well, let's see if first from the audience we have like some questions. Otherwise,
one question here.
Okay,
please.
The question is like, do you need to rebuild the map? And if yes, how often do you need to?
Okay, here they asking if do you need to rebuild the map, and if this is the case, how often it has to be done?
So thanks for the question. Actually, I didn't have time to go into the details, but in this case, for vineyards, you do not need to rebuild the map because of the crop that we are considering. So in this case, once you have collected the images and you obtain the maps, either the 3D point cloud maps or the simplified map, you can use always the same because they are perennial crops. So in this case, you can use the same maps over and over, and you do not need to reproduce the same procedure again over and over during time.
Okay, thank you very much. So now
yeah,
I'm leaving.
Let's thank Martina. I think let me just say that this is a very good example where engineering can join with agricultural science, so to tackle the problem from different perspectives in order to get very, very good results. This research aligned very well with the one we are doing here at the Polytechnic of Bari. So I will be happy to later on to discuss further. Unfortunately, I'm sorry also for Professor Quaglia, there was another question from the audience, but we didn't have the time to discuss. So this shows, however, there is a growing interest towards these topics. So, but we need to move on, unfortunately. So let's thank again Martina, and let's move on to Carl. So let me introduce Carl von Ellenrieder, who will present the current ongoing research at the Free University of Bolzano. If Carl is ready,
are you able to hear me?
Yes.
Okay, good. Thank you very much. So I'm just going to talk very briefly about agroforestry robotics for alpine environments as we're studying them here at the Libera Università di Bolzano. So this set of slides and the work that we're doing is basically in collaboration with Professor Renato Vidoni, who's also here at the University of Bolzano. Let's see. There it is. Okay, so our lab was only inaugurated, say, on the 1st of July. So I just wanted to say a few words about the lab. Firstly, basically, it's a large capannone. You can see it's close to 3,000 square meters or something like this. And our section is here. So we're part of a technological park called NOE here in Bolzano. So Professor Vidoni and myself are directing the lab, and currently we have a couple of assistant professors working with us, Giovanni Carabin and Helen Henninger, and several postdocs and so forth. So just to introduce the lab a little bit. So the main focus of the research that the lab is doing is essentially the development of robotic systems for alpine environments. And just like most other robotic environments, these environments are also uncertain, dynamic, complex, highly variable. However, one thing that differentiates the environments that we find here in the regions in Alto Adige and Trentino is basically that many of the robotic systems that have been developed for agricultural applications have been developed often in the United States or other places where large areas are essentially very flat, and essentially farming operations tend to be done on a very large scale. So in contrast here in this part of, or in this, at least here in this region in Italy, the farming operations tend to be done on a very small scale, usually by family-run farms. Of course, they often occur on very highly sloped terrains, very steep. So there are problems with stability of the vehicle. You also get communications and positioning, dropouts with GPS and so forth. And so those are some of the challenges that we're essentially facing here. So the lab is essentially, the main mission is to be a link between applied research and in essentially mechatronics and industrial automation with agroforestry. And I guess I'll just kind of move into the sorts of systems that we're working with now. So at the moment, we effectively have 3 main ground vehicles that we use. We use a Husky unmanned ground vehicle, which is a 4-wheel system. We have it outfitted with a couple of different robotic arms. So we have a UR5 and UR3. And I'll explain a couple of the projects that we're running with this system here. We've developed a couple of our own systems as well. And this is an example of one where we've taken a 1 meter long remote control scale model, and we've instrumented it with sensors such as RTK GPS, inertial measurement units and things like this to kind of build our own vehicle that we can use in this environment to do some initial testing. And then we also have a system that looks like this, which is a tracked vehicle. It's called the Matrobach. It's made in Austria, and it has a payload of like 500 kilograms, and it's actually quite fast as well. And then we've also just started to experiment with using legged robots, especially in environments like this one, which are very uneven and steep. There are some advantages to using legged systems. And we've only just started working with this vehicle, so it's something new to us. So having said that, I wanted to maybe talk about a couple of specific projects that we've been working on. The first one is, let me see if I can move this out of the way. I don't know that I can. Anyway, I'll let it block it. But in the first case, we've been looking at the use of modular reconfigurable robots. And the main motivation for this is that, a lot of, as I mentioned before, a lot of the farming activities that are conducted in this region tend to be done on very small scales, usually by families and things like this. And so one of the problems is it's very difficult for them to essentially acquire different types of robots or different types of machines to do different tasks. So normally, in a farm or a vineyard, you might need to do crop inspection and monitoring, spraying, and harvesting. And so our idea is that if you could build a vehicle that is essentially modular, you would only have to buy one vehicle, and then you could reconfigure it to do different tasks on a small farm. And the vehicle should be somewhat, the reconfiguration of the vehicle should be somewhat automatic, so that no reprogramming is necessary and so forth. So it should be automatically reprogrammed. So with this approach, we've essentially been looking at a few different tactics. One of them is essentially using dynamic programming to reprogram the system when it's reconfigured. So we can mount the arms, for example, in different orientations. We can mount a sprayer on the end of the manipulator. So you can see here we have the Husky with a manipulator on it. And when we do that, the system should essentially reprogram itself without a farmer having to manually intervene and reprogram it with the new dynamics, say. One of the other things that we think in the long term, and I'll maybe expand on this in another slide, but we feel that in environments like this one, which are highly unstructured, which have a lot of changes. So if you ever watch agricultural operations, you see somebody drops a large, say, bin in the middle of the field, and then they come back and they pick it up, or the truck drives over down one of the vineyard rows, and then suddenly there's a giant muddy rut, and then the vehicle has to navigate this, of course. So we've been also looking at trajectory planning and trajectory tracking in these sorts of environments, as well as human and robot interaction. We think that a lot of these applications could benefit from essentially supervisor level oversight. And so in this case, a person would take over the control of the robot temporarily. Maybe, for example, you have an experienced farmer who knows what to look for when you're doing crop monitoring. That person could temporarily take control of the robot and have a closer look at one or two plants, and then when the person's finished examining them in detail, could release the robot, and the robot should resume doing what it was doing before. So this is an example of some recent experiments. These are all indoor experiments because we've only just started this project, but we've essentially been looking at path planning with obstacle avoidance. And one of the ricercatori who's working with us essentially had been developing path planning methods using boundary node and path enhancement methods. And he's combined this with online path optimization for essentially obstacle avoidance. So in these experiments, the vehicle is essentially moving around an environment, which in this case is a simulated vineyard with these tapes essentially marking the rows of vines. And the idea is that you can put an obstacle in the path of the vehicle. In this case, this obstacle is only seen virtually. So the vehicle doesn't currently have the sensors on it, but it already has the capability to replan the path in real time to avoid the obstacle. And so you can kind of see the sequence where the robot approaches it and then it backs up and it goes away, it comes around the other side. So as I was mentioning before, one of the other things that we believe is going to be fairly important for, say, the widespread use of robotics in agricultural applications is essentially semi-automatic control, where you have mixed input, so mixed control input coming from both a human and from the automatic control system itself. And these are some experiments that we did with that small dune buggy I mentioned earlier. So the vehicle looks like this, and we've essentially outfitted with GPS sensors and its own sort of automatic controller and an RF modem to communicate with a base station, where a user can use a force reflexive joystick to provide input into this. And so we're using what's known in robotics as a mixed initiative approach, where the signal from the human and the automatic controller are mixed. So it's probably a little bit hard to see, but there's essentially a block diagram of how that works. And so in this particular case, what we're doing here is you can see the experiments were conducted in a large area. So that's a tractor. Each leg of this path is about 40 meters by about 5 meters. And so the system would automatically follow the path. And we were essentially exploring its operation with different types of user input. So the first one we called loose rein, where the vehicle is essentially following the path without any human interruption, but occasionally a human interrupts, maybe to move the vehicle to look at another row of vines, for example. And when the user lets go, the vehicle should resume the original path. So this is called loose rein without lane changing. And then we have other situations with different levels of autonomy where a person could essentially interrupt the path following, the automatic path following, by actuating the joystick for, say, a few seconds instead of just temporarily. And the system essentially would measure the intent using something called a storage function. And when it does that, know that the user wants to switch to a different leg of the path. And so we were able to do loose rein with lane changing, where the person could just actuate the joystick long enough to indicate to the system that that the person would like the vehicle to move to the next row. And so you can see the results of that here. And lastly, we looked at tight rein systems where the person maybe is interested in really doing inspection and having tight control of the vehicle when needed, but then when not needed, the person could let go. One of the maybe challenging aspects of this is ensuring the stability of the system so that the person could essentially take control of the system and go really quite far off of the path. And then when the person lets go, it should return. And so this is an example here where the person's taken control of the vehicle and driven quite far away, about almost 20 meters away. And when the person's released it, it's come back to the original path and started to track it again. This would be an example of where, for example, a person could take control of the vehicle, inspect something. In this case, there's a wall here that you don't see in the picture. But basically, we drove along the wall of the building and essentially had the vehicle move along the wall of the building, and then we let go and went back to the path following. Another thing that we've been looking at in the lab recently is what we call the Spruce Spot. A lot of forestry operations tend to be a little bit wasteful in the sense that when trees are pruned, they're usually pruned by a person, which is sometimes dangerous. But also, what happens is when the branches are cut, if they're not cut exactly right, they tend to form knots. And so when you harvest the trees for timber and things like this, the parts of the tree with the knots tend to get thrown away. And so in order to sort of improve the efficiency or the yield of the trees, for example, we're looking at essentially building a system that automatically trims the trees and could even put sort of a type of gel or medicine that helps the tree heal faster. And so our idea is that we could use a ground robot, like a ground vehicle, to approach the tree and release the system and let the system climb up the tree. So this is a very preliminary version that we essentially realized with sort of like a plexiglass ring and 3 motors. And the idea is that the system looks like this, and it essentially can make its way up the tree and use vision to identify branches and a small manipulator to cut them. So this is sort of a preliminary picture of that. Lastly, here in mountain regions, one of the maybe the monitoring the lakes and things like this that are sort of in very remote areas is a little bit difficult, but it's also very important from an ecological standpoint. So one of the things that we've also been doing is essentially looking at the development of, you could say, an inflatable unmanned surface vehicle. So this is essentially a stand-up paddleboard. The system weighs about, I think it weighs about maybe 15 kilos, so you can carry it, and it actually already has a backpack that comes with the paddleboard. But essentially, we've instrumented it to, at the moment, to do depth measurements, but you can also modify that to do other sorts of water quality measurements. And here in the mountains, this is often, from an ecological standpoint, a very important measurement. And so often people have to do this in remote areas, and making something that you can essentially carry on foot and then make the measurements is something that we've been looking at. So that's it for my talk. I'm happy to answer any questions if anyone has them.
So thank you, Carl, for this great presentation. I don't know if we have any comments from the audience.
If possible, I have a short question. You mentioned the harvesting activity. There is a long discussion if robotics can deal with harvesting in complex environment. What do you think about this? The point is, for sure, it is useful for monitoring and taking sample, but harvesting in a wider sense is effective for you or not?
Well, I think on the one hand, you know, there's usually an important or a critical element of harvesting is the speed at which it's done. And so if you have a fully automatic system, you know, obviously, as long as everything is perfect, you can go in and you can harvest very quickly. But I think probably from a practical standpoint, you're going to want some sort of a system where even maybe it's semi-automatic, where maybe 70 or 80% of the things that need to be harvested, of fruit, for example, the grapes that need to be harvested, maybe you can use an automatic control system to identify whether or not they're ready to be cut. But perhaps if you had some sort of a semi-automatic system, if there is a doubt, then the robot could ask the human for advice, and if it looks like it's good enough, and the person could be remotely located. The person wouldn't necessarily need to go there. So you could set up a system where maybe images are transmitted back to a base station, and maybe that could also work so that you didn't need a fully automatic system, but you had some sort of human input, somebody who's experienced in understanding whether or not something's ready to be harvested.
Thank you.
Okay, thank you, Carl.
Thank you.
Sorry, but again, we have a very tight schedule, so we need to move on. But let's thank again Carl for his nice presentation. So let me introduce now Beniamino Gioli. So please, Beniamino, can you turn on your webcam? Okay, so Beniamino will talk about a current project related with digital and sustainable agriculture. So the floor is yours. Beniamino, you can start with the presentation.
Yeah, do you hear me? Do you hear me and do you see the screen?
Yes.
Okay. Thank you, Giulio, and thank you to all the organizers for this workshop. I will report about a project in which actually also Giulio is involved. Is a large-scale industrial research project on the agri-food sector. So we are trying to merge engineering and agriculture companies with research institutes into large-scale projects. There is only my name here because all the names of the people involved would be too many, but I have to thank a number of people. And as you see, we have a bunch of different CNR institutes belonging basically to different departments, but basically the big part is on the agriculture department and the engineering department. Then we have the ICT's company, the engineering section, some universities and agencies, but then we have the agriculture companies. And here we did an effort to put together the big players in Italy, which is Bonifico Ferraresi is the largest farm in Italy, which now is about 9,000 hectares of cultivated surface. We have large groups in the vineyard and in the hortofruit sectors. These are more cooperative organizations that link together a large number of companies. As you say, as you know, in Italy, agriculture companies are pretty small. The average size is small. And so the point is how technologies can be scaled and can be introduced into also small companies. So we think that putting together these cooperative entities is the right way. So we are trying to develop technologies and solutions and hopefully to scale them up in the next future. Then we have also some smaller scale companies in which we apply some pilot applications. All this is based basically in the southern Italy and in different regions. And the overall objectives of this project, which is called eCrops, is to development of digital agriculture and agriculture 4.0 in southern Italy. So to develop technologies and methods to manage the crops and to manage also the risks they are exposed to. And then apply these technologies into pilots. So do real measurements and applications in specific crops, specific companies, having each specific needs. And then try to convert this into decision support. So how to go from the data and from the information to decisions and to management choices. And the work package is basically on the top part is on developing the technologies, and then the bottom part is on applying the technologies. We are so the logical scheme can be seen as a sensing part, which is basically IoT sensors, but then also computer vision and a lot of remote sensing. When we have a phenotyping part, phenotyping means extracting the phenotypes, so the characteristics of each plants in a certain environments to extract the traits of the plant, and then this is the information that has to be organized and managed to be traduced into decision support. So basically, how is robotics related to this? In all the first part, so it's relating to sensing, into phenotyping and extracting traits. If we think of robotics in a wide sense, in which also the data processing and extraction of the information is part of the game. So we are developing a number of sensors and technologies that goes from IoT network to optical gas sensing and in vivo sensors or computer vision sensors. And then we are developing rover and drones specifically for the applications of the project. And this is a phenotyping platform, how it works. So this is basically is a robotics platform, but is a well-established industrial plant. So this is the Italian node of emphasis, which is a European infrastructure on plant phenotyping. So what we do here is to create in control environment, create the link between plant phenotypes and digital representations, which can be image or can be spectral signatures. And so basically in this platform, we generate stress conditions on different genotypes, in this case of tomato, when all the plants are individually monitored and moved along the plants, and then they go in these rooms in which there are computer vision cameras. Plus, we added an hyperspectral cameras, and so we can take digital representations of each plants and extract the information that we need to derive a plant traits. A plant traits can be a characteristics like the yield or the leaf area or the chlorophyll content and what else. So basically, we generate the stress, which is abiotic. So in this case, we created a drought stress on tomatoes, which is biotic. So we introduce a pathogen to infect the plants in control environment. And then we measure how the response is in control environments. Then what we are doing is to putting all this into field environment. So in Sardinia, in a Bonifiche Ferraresi farm, which is about 1,000 hectare farms, we are organizing an experiment that will happen this year in next season, in 2022, which is to put a number of plots and replicates, and again, generate stress, generate different fertilization rates, and monitor them with robots, ground robots, and the UAV, with technologies that goes from computer vision to hyperspectral remote sensing. We put an effort on this hyperspectral because many of the participants has this background. So we have hyperspectral cameras on board the drones, and we have a link with an hyperspectral satellite mission, which is Prisma, which is led by the Italian Space Agency, with the aim to upscale. So what we learn and what we developed into the link between plants and remote sensing data, we try to upscale with satellites to a larger scale, which fits to a company scale, since not any company can be monitored entirely with robotic platforms or drones. Then we have other pilots going on, which involve robotics. Basically, in this phase, we are developing the protocols, and so we sample the plants manually, and then on the other hand, the robot platforms are being developed. So we are doing the pilots to retrieve the 3D geometry of the canopy, so to retrieve data about biomass, but also to retrieve data about, in this case, about olives, which are related to yield, to maturity. And basically, we are going in the directions that the companies are asking. So the agriculture company know where the added value is. And basically, the project is trying to develop technologies to fill gaps in the actual crop management. This is another example in kiwi. Kiwi is cultivated like this. So this is a photo from the bottom to the top. And what is crucial for this kind of cultivation is having yield estimates, so counting the fruits, estimating the dimensions, and also, if possible, estimating the maturity, which is even if it's a less important constraint. So we developed the protocol for ground applications, and we are going in this season to apply it using rovers that are developed by different groups, including Giulio's group in this project. Then coming out with estimates of counts, size, and basically mapping the potential yield of the cultivation before harvesting. So I'm done. The project is in the initial phase, so I don't have final results to report. You can find more information on this website. You can reach me at this email, and we hope to have more results maybe in the next year. Thank you.
So thank you very much, Beniamino, for this nice presentation. And it was nice to see some of our robots in action also, as you said. I don't know if do we have questions from the audience? Eduardo, I don't know if in Rome we have questions from the audience.
No question from Rome.
Let me just say once again that this is a multidisciplinary problem, so it's good to tackle this problem from different sides. So once again, it is important to join engineering background knowledge with agricultural science background. How easy is, Beniamino, to join these two different souls, like engineers working close to agronomy?
Yeah, that's the challenge. So it's not easy because farmers are not always keen to receive or to change how they manage their crops and their company. So yeah, this is the challenge, and we need the right agri-food companies to do this, and hopefully to scale also to the others that are not ready yet. So Bonifica Ferraresi is an example in which they invested a lot of money into precision farming since several years. So they really put the investments, and they really want to extract the value from those investments. So that's a good case, but that's also a unique in Italy. So they are really large, and so they can do investments that other size of companies cannot do. So the challenge is this. And I think also with companies that are in the project that initially were not so available to change things, the process is changing. So I think also overall in agriculture in Italy, we are in a changing phase. So there is a lot of exchange of people. So new generation are starting to, or restarting to cultivate fields and to establish a small scale farms. So, and they are much more available to receive the technologies and also to change the way they manage crops. So the innovation technologies are going to change the game quite a lot in these years, in the next years, I think, at least in Italy.
Okay, thank you very much, Beniamino, once again. Let me introduce now Enrico Di Maria, who is with the Kyushu Institute of Technology. He just finished his PhD. So Enrico, are you there? Can you share your screen, please?
Yes. Can you see my screen?
Yes, okay.
Okay.
So whenever you're ready, you can start.
Okay. Good morning, everyone. I'm Enrico Di Maria from Kyushu Institute of Technology. And first of all, I would like to thank the organizers and especially Professor Giulio Reina for the chance to talk here today. And my presentation is comparing FEM and experimental data to predict rolling resistance in grape transporting vehicle. So at first, I want to give an introduction and explain about the main motivation of the research before going to the real target over this talk. And so talking about soil modeling, the experiments in the vineyard, our model, and the results in discussion. Okay, so can you see the title?
Yes, yes.
Oh, okay, okay. So as you probably know, wine, Italy is one of the main producer of wine, and in 2019 it was the main producer, and so this is an important sector for our agriculture. And usually the traditional way to harvest the grape into a vineyard is that some workers collect the grape and put in this basket. Then a tractor with a cart enters into the field to collect the grape, and finally he is going to fill the main truck outside the field. And since the harvesting period usually is August or September, and we have some rain, some heavy rain, it's possible that when we must collect the grape, the field is not in a good condition. So having this tractor entering the field can cause huge damage. And in fact, as we know, the soil is a porous medium. It consists of particles. And we have two types of damage when the vehicle passes. So the first is called soil compaction. So when they will pass, these pores are compacted, and so there is a volume change. And this is detrimental for the soil because the water cannot infiltrate, and also the roots cannot grow. And the second mechanism of damage is soil distortion. This is especially important for running gears that have a longer contact patch, for example, a track system, because the particles are taken from the beginning and then displaced along the whole length. So this is a second mechanism of soil damage. And so the result is that we can see these ruts in the field, and the farmers must restore the soil quality, and so this represents a cost. And so the main scope of the research is that we are thinking about developing a system that can adjust the contact area based on the soil condition and also on the payload. So basically, it can go from half-tracked mode to a wheeled mode, so reducing the area in the second case. Besides the damage to the soil, this is of course is going to change also the performance. Usually on soft soil, the track can perform better, while on hard soil the performance became more comparable, especially on frictional soil. But the wheel mode is how to say, more efficient. The steering is more efficient if we use steerable wheels. And so eventually the final image is that we should have some autonomous cars working alongside with humans in the field. And the base, for example, of some soil moisture information, and also, for example, the current drawn from the motors, which is roughly proportional to the rolling resistance, the vehicle should decide which locomotion system is the best for that condition. And so we go to the target of today. So today, what I'm going to do is I will talk about a FEM model that we developed to analyze rolling resistance and ruts formation. This is to support the design of this prototype. And I will also show briefly some experiments we carried out in the field to investigate the mechanical soil properties. And finally, we will evaluate the impact that different running gear size have. And I'm going to focus on the wheel type, which is the simpler case. But I want to mention soon that this actually this analysis belongs to a broader context of experiments that includes also the track. And at the end of the presentation, I will say just briefly something also about the track. So we consider as target firm soil, soft soil, and wet soil. To model the soil, we need at first to define a yield surface that is a boundary between the elastic region and the plastic region, because the soil is an elastoplastic material. And the Drager-Prager is often used for modeling the soil, because there is a dependence from the hydrostatic stress. But we use also the von Mises, which is this cylinder, and usually von Mises is used for steel. And the Drager-Prager is apt to the firm soil and soft loose soil, so when we have volume change. While for wet soil, basically we have distortion, so for this we prefer the von Mises. And so to characterize these surfaces, we need to estimate some soil parameters. And for doing that, we carried out two kinds of experiments in the field. One is the compenetration test to estimate the elastic, frictional, and cohesive properties. And the other test is the pull test to have a comparison with the FEM simulation. This to measure the rolling resistance and the sinkage. And so we use this compenetrometer is a tool to measure the strength of the soil, and the moisture sensor, and the basic gauge force for measuring the rolling resistance. And finally, with a simple caliper gauge and hold the plexiglass plate, we are going to measure the sinkage. So at first, we prepared the soil in the condition we wanted. For example, in the picture on the left, you can see the soft soil. And we marked a series of points where we have to carry out the measurements with the cone penetrometers. And finally, based on these results, we can try to estimate the elastic properties and the plastic properties. There are some relations that I don't show here. Then we carried out the pull test. We developed this frame that we attach behind the tractor. And you can see here there is a steel cable with a force gauge that is connected to this portion of the cart. So the cart can slide and is basically pulled by this steel cable. And then we can adjust the weight with these cast iron discs. And we used two sets of weights, 50 kilograms and 80 kilograms. And we use an airless tire because we want this wheel to act as a rigid wheel because we are interested in the deformation of the soil. And with this experiment, we measure the rolling resistance and the sinkage. So after the wheel pass, using the gauge caliper, we measure the sinkage in the field. And so, thanks to the experiments, we could tune the parameters in the FEM model. And here I show just one of the results. This is for the 80 kilogram on soft soil. In black, you can see the resistance coefficient, while in red, the sinkage. And the dashed lines are the average from the experiments, while the gray lines are the standard deviation. And we can see that the rolling resistance is has a good match, while the sinkage is a little bit underestimated. This happened also for the other cases, and probably because the soil in the model is a little bit stiffer than the real soil. And finally, we consider the range of diameter and width that we want to investigate based on our image of the final prototype. And we also assume a final weight. We assumed 400 kilograms, including the payload, so including the grape. And we assume this weight to be uniformly distributed, so 100 kilograms for each wheel. And so what we got also here, I show the results only for the soft soil. So here we can see some the response surfaces for sinkage on the left and the resistance coefficient on the right. And the dashed line is on the left, again, the resistance coefficient, while on the right, the sinkage. So basically, I superimposed the two response surfaces, one on each other, just to compare how the width and the diameter is affecting these outputs. And the result is that the diameter has a better impact on reducing the rolling resistance, while the width is more beneficial for reducing the sinkage. And possible explanation of this is that since the rolling resistance depends on the volume of soil deformed, if we increase the width, is it true that the sinkage is decreasing, but at the same time, the area, the portion of soil engaged with the wheel and deformed is larger. So probably that's why we have this result. And finally, we assume an operating velocity, 0.5 meter per second, and we easily evaluate the power loss. So the trend is exactly the same of the rolling resistance because it's rolling resistance time velocity. And here on the right, we can see also the maximum stress at the contact. And of course, I forgot to mention, increasing the contact area is always beneficial. As long as we keep the same weight, of course, we should consider other design constraints. And as I said, I will give just a very brief information about the track module because we also carry out some experiments related to the track. So in our laboratory, we developed this track, and then we connected it to a frame similar to that we saw for the vineyard in Italy. And since because of the pandemic, we could not go to carry out the experiments in Italy, we built our own facility. So we mixed the main components of soil, which is clay, sand, and silt. And we got as much as possible an agricultural soil. And then with a compactor machine, we adjusted the strength. And then we carried out again the analysis. You can see on the left that this track is quite simple, very simplified. The reason why we started with this simple system is because modeling the track, especially in a 2D model, 2D FEM model, is quite difficult. So, and also it must be parametric, so this dimension must change. So we started with this, but you can see that the pressure bulbs are too uniform. So this somehow, with this model, we underestimated the real pressure, and all the rolling resistance and sinkage were underestimated compared to the experimental results. And so now we implemented a multi-body model where there is a flexible chain. So you can see now we can see correctly the peaks of stress under the track. But here now we have a simplified soil. This is an elastic soil. So the next step should be to have a synthesis of these two models and complete the analysis of the track that is still ongoing, basically. And so in conclusion, in this talk, I introduced the concept of a reconfigurable locomotion system. And I showed how we carried out some experiments in the vineyard to investigate the soil properties to tune the FEM model. And finally, we carried out an analysis to evaluate the impact that diameter and width of a wheel have on ruts formation, rolling resistance, and power loss. And this is all. Thank you for your attention.
Thank you very much, Enrico, for this nice presentation. Just one quick questions, please. Maybe you have one?
Yes, one. Thanks for your interesting presentation. It gives useful data for design, so it is very interesting. It is close to what we have done. The route is the same. So in our case, we choose to have an 8-wheel in contact with the soil for the same reason that are pushing you to have a reconfigurable track. What do you think about the 8-wheel solution, since you are an expert?
Thank you so much for your question. And I don't consider myself an expert, but anyway, I think, yes, I've read a paper about that system recently, so I knew it before. Because now we are designing the switching system, and I think there are some interesting information about your system. So yes, I think that the 8-wheel system can have some advantages over my system, because when I switch from track to wheel, that is not a real wheel, and the real behavior, that's something that we should evaluate experimentally. We don't know really it will act as a wheel. Also, there is some internal friction that is connected to the track module itself that we cannot avoid. So I think also the idea of using 8 wheels is very interesting. Maybe the track system can distribute better the pressure, but of course that also depends on the size. So difficult to say a priori.
Okay. Thank you so much, and I wish you to have a successful result on your study.
Thank you so much. Thank you so much.
Okay, so sorry to interrupt this interesting discussion, but unfortunately we are short of time, especially because we are now finished the first section and ready for a coffee break. So please enjoy your coffee that is virtually offered by the organizers, and let's see us back in only 5 minutes. So we will start again at 11:30. See you soon.
See you later.
So anyway, I would like to invite Luca Bruzzone to join the session so we can start this second part of the workshop.
Thank you very much, Giulio.
And so I will start this second session, and that will phase rather than agricultural applications, we will face general problems related with robots that need to operate in highly challenging terrain. So Luca will show us some nice examples of this. So please, Luca, go ahead with your presentation and see you later.
Thank you, Giulio. Good morning to everyone. Now I share my screen. This presentation is about a hybrid locomotion system for small-scale ground mobile robots. If we try to put in a qualitative way in a plane where in the horizontal axis there are speed and energetic efficiency, and on the vertical axis there is mobility in unstructured environments, we can place the main locomotion system, legs, tracks, and wheels, and there are 4 possible hybrid combinations. Legged robots are in this zone of the plane. Wheel robots are in this zone of the plane. Track and robots are somewhere in the middle. And if we want to try to go in this good zone of the plane where we can conjugate mobility and speed and energetic efficiency, we can use hybrid locomotion systems. If we consider medium or large scale ground mobile robots, legged locomotion is probably the most performing solution, but high-end legged robots with dynamic aid are very costly and are very complex to be controlled. So in case of smaller robots, where inertial forces are less relevant, and so it is possible to accept higher motion discontinuities, it is possible to adopt simplified hybrid architecture, for example, rotating legs and so on, or to conjugate legs, wheels, and tracks as in this azimuth. These examples are well known in the scientific literature, but I will focus on the mobile robots that we have developed at the Mekai Lab of the DIME department of the University of Genoa. I started to work on mobile robots thanks to the collaboration with Professor Quaglia, who is the inventor of the EPIQ mobile robots family. And with my group, I worked on dynamic multibody modeling and experimental prototyping on this family. Then I will discuss the Mantis robot family and the Whitlock. I am the inventor of these 2 families of robots. And then I will give some hints on the snake track. The inventor is Dr. Shabedino Day. The 2 last works are in progress. This is a video about the EPIC robots, which are based on the strapping triple wheel locomotion unit. This locomotion unit can switch from wheeled locomotion to legged locomotion, rotating the triangular locomotion system on the basis of the dynamic condition, because its mechanism is based on an epicyclical mechanism. So this robot, for example, has only 2 motors. Has only 2 motors because it has only the front wheel which are actuated. But it is possible to use also more complex configuration. For example, these 2 are with front wheel drive, then only 2 motors. In this case, there are 4 motors because all the locomotion system are actuated. While in the front wheel drive configuration, the rear carriage is idle. But it is also possible to complicate, using a modular approach, the architecture of the EPIC family. In this case, the locomotion unit can be placed on the top of some legs. In this case, they are passively suspended. In this case, they are actuated. Mantis uses a different approach. It has actuated wheels with differential steering and two legs which are inspired to the praying mantis leg shape. And the legs are used only in case of obstacles, steps in ascent or descent, or uneven terrains. We used a non-dimensional approach, a non-dimensional analytical approach to study the influence of the main geometrical parameters, but also multi-body simulation. Multi-body simulation has been used mainly to do the synthesis of the leg motion law for step climbing. Here we can see a video about the Mantis robot. Here it is going on obstacles which are quite big in comparison with its size, and here Mantis is climbing a stair. There are also two passive wheels here which are used to reduce friction in the last phase of step climbing, connected with one-way clutches. It is also very maneuverable in narrow spaces, and it can restart from any position, because after a capsize, it can use legs to start again moving. Whitlock is a wheel, track, leg hybrid locomotion robot. It has two actuated tracks with differential steering for tracked locomotion, but it has also two legs actuated independently and two wheels actuated independently. But on one side, there are also two omni-wheels. The robot is fully symmetric with respect to the XY plane. So this robot can be used in this way. On wheel locomotion, he is suspended on the two wheels and on the omni-wheel. So it is fast and with low energy consumption. It is also in a position with the field of view of the front camera is good, because it points up. If we lift up the legs, it is a normal tracked robot. If there are obstacles, it can use also the legs and the wheels to cross the obstacles, for example, on stairs. In this case, the omni-wheels are on the front, so the contact is on the track, on the rear part. In this slide, we can see the multi-body simulation used to synthesize the leg motion, the combined motion of legs, wheels, and tracks to overcome a stair. We are in the phase of prototyping, and here we can see the first experimental tests on stair climbing. The first experimental tests are successful, and this is a very good news that we have achieved in the last days. Snake Track is the last robot that I will present. It is a bio-inspired single-track mobile robot with a compliant vertebral column. It is designed for surveillance and inspection in narrow spaces. It is a single track, so it can steer by bending the vertebral column. The bending is commanded by these motors, which are connected to a wire. There are 2 wires on the 2 sides of the robot, and in this way we can use 2 motors placed at the modules to steer, and the other 2 motors are placed on the ends to move the truck, moving the ride sprockets. The cameras are placed on the front of the robot because there are holes on the tracks. It is not a continuously updated view, but it is useful to guide the robot and to perform surveillance tasks. Due to the holes, we can put cameras also on the top of the track, obviously, if it is required. But this work is in progress. In conclusion, we can say, as already said by Professor Quaglia, there will be an increase in the spread of service robotics. So the development of innovative locomotion system is an important research area. And in case of small-scale robots, hybrid locomotion system a very good alternative to purely legged robots that are very costly and complex to be controlled. In most cases, the design approach is oriented to general purpose robots. In this case, we want to conjugate speed and energetic efficiency on flat and compact grounds, motion capability on uneven yielding terrains, step climbing capability, because if we want to monitor inside the buildings, there are lots of steps and stairs to be climbed. And examples of this approach are EPQ, Mantis, Whitlock. In other cases, it is possible to study a locomotion principle which is tailored to the specific application, for example, snake track for narrow spaces. In any case, nature is always a great source of inspiration. Thank you for the attention. Is there any question?
Thank you very much, Luca, for this very interesting presentation. Are there any? Okay, so I see now Dario and Eduardo. So, any questions?
Can we ask a question from Rome?
Yes,
yes.
please.
I was wondering, the first kind of robot you showed, the Mantis, I guess it was called. If
this is this one.
Yes, exactly this one. Is there a way, a model-based way, or another way that the robot is able to understand if it's able to do a climbing operation beforehand?
Okay. In our lab, we are focusing on the mechanics. We don't want to spend our work to do something that is done better by other researchers. I am a mechanical engineer and I am focused on the mechanical aspects. However, obviously it is possible. We have worked on the Mantis with full radio control, but for example, but it is a limitation because it is not always possible to be very repeatable in the step climbing. For the other robot, our approach for the Whitlock, for example, we have put a Maio inside the robot. All the motors are connected to encoders, and the encoders are connected to the Maio, so it's possible to plan the motion of the motors in order to perform correctly and in a repeatable way the step climbing motion. I don't know if I have answered to your question.
Yes, I guess so. Thank you.
You're welcome.
Let me just add something, because it's interesting to see that you have a reconfigurable robot very similar to the one showed by Enrico before. So it's nice to see that in different parts of the world you had the same idea of having a robot that can work with wheels or with a truck. And just this consideration.
Thank you very much.
Okay. So Eduardo, I think we can move on. So I'll leave.
We can move on
pass the ball to you.
Next presentation, which is mobile robotics for service application, and the presenter should be Rocco Galati. Is he here?
Yeah.
Okay, you can share the screen and the floor is yours.
Yeah. So you should be able to see my screen, I guess. Okay.
Yes,
right.
we have it.
So my name is Rocco Galati. I'm a researcher at the Robotic Mobility Lab, and today I'm going to have a very short presentation about mobile robotics for service application. So this is a showcase about some of the robotics platform we designed at our laboratory. Let's start by saying that when we speak about service robots, we usually speak about machines able to assist or support human operator while performing jobs that can be dirty, dangerous, or repetitive. Here we have 4 different types of robot. Picture 1 and picture 2 represent 2 mobile platforms based on rubber tracks. The first one is with suspension, while the second one uses very large tracks to roll over this kind of material, which is very similar to sawdust, in order to compress it. And then we have also this other robot, which work inside the exhibition building. And the main application is to put on the floor some mats that are the perimeter of the booth before the exhibition day. And this other robot is similar to the first one, since the robot in the first picture and the fourth picture are just general purpose platform, which can be used to carry sensors or devices, maybe for monitoring application in agricultural field. The only difference is the robot in picture 4 is based on wheels, while the first robot is based on a tracked undercarriage with suspensions. So going more in details about the robot for the exhibition, we can see that it uses mechanical wheels because the main application is to make the robot be able to move in any direction by minimizing the slipping effects. So in the upper part of the frame, we have placed 2 paint tanks, and we have also an air compressor that can enable or disable the bottom sprayer to enabling painting operation. On the left side, we have a typical application for this robot. This is a plant of a booth, and the red lines need to be marked on the floor for each pavilion. So for each exhibition building, we have different pavilion, and the robot needs to trace all these red lines. Usually, the robots at the beginning start to mark all the vertical lines and then the horizontal lines by using some kind of routing algorithm in order to minimizing the overall time needed to accomplish this task. I have some videos to show. Hope you can see them. So this is one of the first tests. The robot is running inside a pavilion. As you can see.
Sorry, Rocco, we don't see the video.
Oh, I don't know how. Maybe I need to stop and share again. I don't know.
Try to stop and share again because you are maybe sharing only PowerPoint.
Okay. So now it's better?
Yeah.
Okay.
Okay. So the robot is moving inside the pavilion. As you can see, is tracing a gray paint over the ground. During this test, the robot is teleoperated because it was just a test to see how the paint is landed over the ground. And also by using the mechanical wheels, the robot is able to steering over a very fast surface without slipping effects. And so come back to the presentation. I have other videos, but I think we are running low on time, so I skip them. And so in this slide, we can see the problem we were able to solve with the robot with large tracks. It was the robot in the picture number 2. So the problem to solve in this case was to be able to increase the bulk density of the material. This is very similar to sawdust, the material after the wooden production. And the bulk density in this case is defined as the maximum number of flux sheaves divided by the total volume that they can occupy inside the truck container. So this is the container, this is the material, and we have a mechanical hopper placed at the top of the container with a screw feeder that make the material fall down. To solve this problem, we designed this really heavy machine with wide tracks. Each belt is about 80 centimeters wide. And this is a picture of the robot in action. So as you can see, we have the material falling down from the mechanical hopper and the robot is rolling over it. And on the right picture, we have the result. As you can see, the material is all compressed. And I try to show you the video. So
Same problem.
Yeah.
Try with just the combination
Yeah.
of Alt and Tab.
Yeah, I guess
okay.
now you
Yes.
Okay. So the material is falling down, the robot rolling over it by compressing. This is the first layer. And basically what the robot does is floating over the material. So it's for this reason that we designed these wide tracks. At the same time, the robot have to avoid to have too much pressure on the fiber of the material in order to avoid to destroy them. In this slide, we can see one of the most important feature of the tracked robot. So I'm speaking about the suspension system. This is one of the first tests we ran in order to test the suspension. We used a wooden obstacle. And as you can see in this picture, we see that when the robot starts to face the obstacle, the wheel B goes up while the wheel C goes down in order to keep the belt tightened. This is very important because in this way we avoid the belt to pops out from the undercarriage. And if this happen, then the locomotion system can be blocked. So this is very important to keep the belt always tightened. And the same happen also when the obstacle is at the bottom of the belt. In this case, the wheel C and wheel B moves in order to keep always the belt tightened. This slide shows our 2 recent robots. Also, the robots with wheels as a system with suspension. In this case, we have 2 swing arms, the red ones, able to pivoting around the central axis. Moreover, this robot is able to provide different driving styles. For example, here we can see the robot while moving sideways. And in this other picture, we can see the robot turning on the spot. with this general purpose platform, it is possible to face different kind of terrains. And because of the high payload, it is possible to carrying several sensors, as you can see in these two pictures. Moreover, it is possible to use a combination of this platform in order to implement some kind of collaborative robots routines. And this is very useful, for example, if you need to monitoring a large field in agricultural application. Moreover, by using, for example, all sensors and inertial sensors, we are able to detect and extract the terrain feature. In this slide, we can see how, by comparing the current drawn by the motors, we are able to discriminate several kinds of terrains. For example, we can see that sand drawn much current compared with the asphalt, and the same, we can do the same also by using the inertial sensor to analyze the vibration along the z-axis in order to compare different soil conditions. Usually all of our robots run over ROS, which is a framework for robotics system, where each sensor is a node and its output is a topic. All this communication is made with a main node, which is able to elaborate all these data and perform high-level application. Typical sensor set can include encoders, inertial sensors, GPS, usually RTK GPS for accurate positioning, and depth cameras and laser sensor for obstacle detection. By speaking about the software, we run always on ROS, and we have a main node able to communicate with lower level routines, usually used to control the motors or to communicate with encoders or sensor and so on. And also our main node is able to communicate with another level of software routines, able to keep the output from inertial sensor, lasers, and RTK GPS. By combining the output of all these sensors, we are able to improve the positioning of our platform in the field. And by using the camera, we are also able to run a three-dimensional mapping and also the terrain classification. As a result, we can see here a 1 yard reconstruction while the robot was moving along this 1 yard row. We were able to put a label on the building map, and as you can see, the robot starts facing the soft terrain, then encounters a flat surface, a plowed one. Then here there is a little bump detected by using the inertial sensors, and then mud. All these labels were put in during an online classificator algorithm. So I'm done. Thank you for your attention.
Okay, thank you very much, Rocco, for your presentation. We are a little bit behind schedule. Maybe if there is one very quick question from the audience.
Very short one related to the wheeled rover. Okay, this one. Talking about the suspension system on the top image, can you give us some more detail? It is passive, active, or something else?
It's passive in both the robots. So both the truck and the wheel robot use passive suspensions. In particular, the robot with wheels use in a total of 4 springs to keep the both swing arm balanced all the time.
Okay. More detail in a separate way. Okay,
yeah,
thank you.
Unfortunately, I don't have a drawing about the suspension of the wheeled robot, but you just have to think that the rotation axis is in this position, and both arms are connected together, so one can work at the contrary of the other arms. So if these arms goes up, the other arms will go down. And this is all passive, so we just use springs.
Okay, thank you so much.
Well.
Okay, so thank you again, Rocco, for your talk. Now let's go ahead and introduce the next work, which is entitled Under-Actuated Cable-Driven Parallel Robots as a Crane Stabilization Tool by Edoardo Ida and Marco Caricato, who are actually two of the organizers of this workshop. So I will give immediately the floor to Edoardo Ida.
Okay. Can you see my screen? I hope so.
Not yet.
Not yet. Screen number 2. Maybe. I already.
Okay.
Okay. Can you see it now?
Yes.
Yes. My presentation as well.
Perfect. You can go ahead.
Okay. Yeah. Okay. So, hi everyone, I'm Edoardo Ida, and I introduce you to our recent work on under-actuated cable-driven parallel robots as crane stabilization tools. After a brief introduction to what a cable robot is, and specifically an under-actuated cable robot is, I'll briefly recap what are usually crane operations and their main limitations, and show how an under-actuated cable-driven robot can be envisioned as a multi-cable cranes. Then I'll show some of our latest simulation result for achieving crane-like operation and thus limiting standard crane shortcomings. So cable robots are parallel manipulators that use cables to manipulate an end effector in space instead of rigid links. And among their main advantages, they are easily reconfigurable by just changing the cable exit point. And their workspace can be scaled up to several cubic meters. They also can achieve considerable speed and acceleration. They can do very dynamic motions since cables are practically negligible in mass. On the other hand, unfortunately, since cable can only pull and not push, there are usually more cables than the end effector degrees of freedom, since this can allow to achieve better control of the platform. An under-actuated cable robots instead employs fewer cables than the end effector degrees of freedom they control and rely on gravity to maintain cables taut. Their design is thus mechanically simplified with respect to cable robots that have cables all around the platform, and the workspace accessibility enhanced. On the other hand, fewer cables also means less controllability of the end effector, whose pose depends on both kinematics relations imposed by the cable on the platform, but also on the mechanical equilibrium of the platform as well. In addition, less cables also mean less constraint ability. Thus, arbitrary forces may excite large arbitrary motion if they are applied on the end effector. End effector oscillation may be limited in real time if we use, for example, feed-forward control approaches, such as input shaping. Or they can even be completely eliminated if uncertainties are limited and special trajectory planners are used, such as rest-to-rest planners, as in these videos. So how can we use a cable robot as a crane? Basically, cranes are the simplest cable robot you can envision. They have just one simple cable, which is used to lift vertically a heavy payload. And secondarily, by using other kinds of actuators, which depends on the type of cranes you're using, this kind of payload which is lifted can be also displaced horizontally. One of the principal limitations of the cranes is the fact that the lifted payload may swing due to several factors. Crane operators are in charge of the safe manipulation of the payload, and if they are having a bad day, things can go sideways very easily. Please note that the payload that the cranes are lifting may be people, as in this video we are showing. Sorry for the noise. See, if the crane cable exit point is moved, for example, in a displacement operation, or as in this video I was trying to show, if the frame is mounted on a ship, there is practically no chance that the operator can react in real time and compensate for this kind of disturbance. And this is the harsh environment we are envisioning our cable robot to operate in. In collaboration with a company based in Bologna named Calzoni, we are investigating if an underactuated cable robot can be used for automatic handling operation from a side of a ship under mild sea conditions. These are mild sea conditions, C4, for example. The cable-driven power robot acts as a multiple, fast and coordinated crane, concurring on the manipulation of the payload. So this new kind of multiple crane can dynamically capture, for example, the payload while it floats on the sea level and avoid or drastically limit the payload oscillation during the lifting operations. So the dynamic capture of the payload requires that the hook mounted on the robot platform here follows a target in space, which is sampled in real time thanks to specialized sensory apparatus. In addition, the use of more than one cable may consistently limit unknown payload swings during lifting operation, even if the payload is completely unknown in mass, shape, and inertia, which may be well worth the cable robot additional cost. We'll now have an overview of some operation by starting from the most simple ideal case. We want to track a fixed target with the help of the robot. And the cable robot is first deployed and then approaches the target. And when sufficiently stable, performs a picking operation. If we complicate the scenario and the target is moving, the stabilizing effects of the cable robot are very effective. And despite the hook is winging, the target can still be picked. If more drastically and also realistically, the crane frame is moving, the cable robot is able to compensate for it. From one hand, the cable robot stabilizes its own hook swinging induced by the frame motion. And from the other hand, the robot keeps tracking the target and then successfully picks it. Of course, it needs to stabilize itself, so it takes a little bit longer. We'll now show some results concerning swing stabilization after a completely unknown payload is picked. Payload swings are significantly contained and lifting cable swinging is eliminated. Of course, the more power has the robot, the more consistent the stabilization will be. This feature works the same way even if the crane frame is moving. And on the contrary, frame motion excites even more dangerous oscillation with a single lifting cable. We tested that this strategy is even more effective if the actual payload takeoff from the sea level, for example, is considered. In this example, we assume that the payload is floating on water and stabilized its lifting as in a sea recovery operation, which is the application we are actually studying. So in conclusion, we showed how an under-actuated cable robot can be used as a safer and stabler crane, theoretically. In order to do so in practice, we are currently working on precise hook and frame motion estimation, and we'll conduct some field experiments soon. Thank you very much for your attention.
Okay, so thank you, Eduardo, for your talk. Very, very interesting. I don't know if there are any questions from the audience here or either from the chat, so from the remote audience.
Oh, in the meanwhile, I have just a brief question, if I may.
Yeah, sure.
Just wondering what are the sensory feedback that you're using in order to stabilize your system? Just the tension of the cable, or also using like a camera or do you need like an IMU in order to read the oscillation of the system?
Well,
Can you
actually,
tell a little bit more about this? I mean, how do you, I mean, what are the sensors or the kinematic quantities that you are monitoring in order to have a feedback and control your system?
Well, in order to perform this task, especially the tracking task, for the stabilization task, they need different kind of requirements. Let's talk about the tracking task, which is actually the more demanding from a sensory point of view. Well, actually, we have a lot of sensor around. We think we will need to implement a lot of sensor around, since we are still in the simulation phase, because we need to track the pose of the end effector, but also we need to track the frame of the robot motion. Thus, we'll need some sort of IMUs or something similar, which can give us an estimation of the 6 degrees of freedom motion of the frame. Then we'll need to also estimate the pose of our platform with respect to the frame. And also we need to track the target we are picking. So there is also a relative distance measure to be performed with the payload we are trying to pick. So basically we have a lot of sensor around. We don't use cameras. We don't envision using cameras, since the sea conditions probably wouldn't allow to a very accurate measure for this kind of task. We are experimenting on radio frequency sensors, for example, for measuring the relative distance from the platform to the payload we are picking.
Thank you very much for your answer and for the nice presentation.
Okay.
You're welcome.
So I think that we can now move to the next work by Daniele Bernardis, Massimiliano Solazzi, Domenico Caradia, Luca Tiseni, and Antonio Fisoni, entitled Mobile Robotics for Critical Infrastructure Monitoring, a work by the Istituto di Intelligenza Meccanica from the Scuola Superiore Sant'Anna di Pisa. And the speaker is Domenico Caradia. Domenico, are you here?
Can you hear me?
Yes. The floor is yours. You are allowed to share your screen.
Okay. Just give me a moment. This one. Okay. 1 second. Do you see the screen, the presentation?
Yes.
Okay. I'm Domenico from the Institute of Intelligent Mechanics of the Sant'Anna School of Advanced Studies, and we'll present you the work developed by the group led by Professor Frisoli on the mobile robotics for critical infrastructure monitoring. And I will mainly present two application of mobile robots for challenging environments. The first one is for predictive maintenance in train cars, developed by Trenitalia. That is the main company that manages the Italian train network in Italy. And why maintenance? Because the emergence of high-speed railways is gradually leading to stricter requirements in terms of safety, availability, reliability of rail operations. And the key goal of the rail industry is to maintain a cost-effective way the monitoring of the infrastructures. So there are three main strategies for the maintenance. The basic one is the corrective or event-driven maintenance, in which a restoring operation is carried out upon the evidence of occurred damage. Then the cyclical maintenance, the most used now, where the maintenance is performed at a fixed time, at fixed time intervals, and the on-condition maintenance, which is meant to predict the potential breakdown of the plant through a regular condition monitoring. So the objective of this first mobile robot is the inspection of the undercarriage railway vehicles in order to apply these condition-based maintenance strategies. So in the literature or in the market, there are very few robotics or automated solutions that can be found. So they require usually special tracks. That means a specific maintenance plant, or they're fixed platform and can target only a specific part of the train. So to increase the number of the monitored trains, the number of the train portions, also the frequency of the inspection, it is needed a platform that can work on normal tracks. So we proposed a mobile robot which rolling system and folding robotic arm design allow the operation on an ordinary railway track. The proposed robot was designed to move on the tiny free space left between the train wheels, the railway tracks on the side and the ground. This robot is mainly composed by the mobile platform, the robotic arm, and the controller. The mobile platform is an aluminum chassis with two independent group of wheels that are connected to it and target two different surfaces. The passive group is composed by four wheels that run freely and sustain the weight of the platform. On the other hand, the active group is in charge of the motion of the chassis, and they are designed in order to fit and to be in contact with the lateral part of the rail. The robotic arm instead is designed to allow the movement of the sensorized head with a RGBD camera under the train and to allow the fully retracted configuration to allow a fast scan of the train or a more slow and dedicated scan of one part of the train. The robotic arm has 5 degrees of freedoms. It is a serial kinematics. The first degree of freedom is a prismatic joint made by a linear guide that allow the robot to span from one side to the other side of the rail. The other 4 degree of freedoms are the rotodal joint. And regarding the control system, this control system is located on the chassis of the mobile platform. How we sensorize this robot? We have 4 encoders on the wheels and the camera on the end effector. And this system can be used in 2 modalities. The more fast one, that is a navigation modality in which the robotic arm is fully retracted, and we can scan by teleoperation by remote operator, or in a semi-autonomous way when we fix some point of interest, and the robot can reach that point, take a picture or some picture in that area, and then go ahead. Or in inspection modality, in which the mobile platform is stopped and the robotic arm can be raised and teleoperated by the remote operator and reach more in detail the surface. This is just drone specs, a very quick overview of the system. We estimate an inspection time per train car of 15 minutes with an overall weight of the system of 60 kilograms. This is an on-field validation made by an operator of the intraitalian operator that autonomously performed this task. He was able to monitor the state of the traction hook dampers, the presence of fixing items, and brake pads. These are the pictures taken of the interested part of the train. The second platform we developed was for the safety inspection of railway. That is a different, is the same environment, but is different because is developed by the is developed in partnership with the Rete Ferroviaria Italiana. That is instead the main company that manages the railway infrastructures. RFA usually carries out maintenance operation during night. So there is the need to inspect the work site after the operation or at the stop of the line, because a work tool or some operation residual can be left and that can result in a possible obstacle for trains. So this means a critical safety task. So we design a robot to automate the inspection procedure in a versatile way and affordable way. We propose this drone that is designed for high-speed autonomous inspection on the line. This is equipped by two lidars okay, that are laser sensor, one in the front and one in the lateral part. It records meaningful data related to profiles and volumes of the track, checks the clearance profile of the loading gauge, and detects frontal and lateral obstacles. From the mechanical point of view, it has been designed with a carbon fiber tubular frame to obtain a low weight and high dynamical properties. The cover was designed to obtain a low aerodynamical drag, and from the motion part, it was implemented by, obtained by 4 independent in-wheel motors that simplify not only the generation of the motion, but also reduce the mechanical components on the frame. I will show you some relevant details of this car that are the maximum operating speed of 100 kilometers per hour, the autonomy at the speed that is 30 kilometers, and the possibility to detect an object of 10 centimeters per 10 centimeters at a distance of 50 meters with a weight of less than 50 kilograms. This is an example of lateral obstacle detection. Behind the camera on the ground, there is a person that simulates an obstacles. And in this moment, the robot stopped and came back to the obstacle and then generate an alert in order to allow the operators to study and to detect the obstacles. The same scene can be seen from another perspective. The obstacle in this case is a man, and the robot detects it thanks to the laser sensor, record the position where the obstacle was detected, and then came back to analyze the obstacle. So in conclusion, we developed 2 mobile robots for the challenging environments, in this case, the railway environments. One for the train undercarriage inspection and predictive-based maintenance, and the second one for safety inspection on railways. The use of mobile robots in railway can reduce the economic loss by maximizing the use of train parts and by reducing the activity of the whole train, and improve the safety of railways and automate inspection process after maintenance operation. And I think these are in agreement with the use, the service of the use of the robot as indicated in the very first presentation of this morning. Thank you, everyone. And if you have questions, you can ask me.
Thank you very much, Domenico, for your talk. So, is there any question? Are there any questions?
If possible, I have one regarding the first prototype that you show us. I was wondering, why did you choose as a first degree of freedom, if I remember well, a prismatic joint? I suppose that is related to the workspace and the condition of interference between the target position of the arm and other things that are around, but I'm not sure. Can you add some more information about this choice that you have done?
Yeah, thank you, Professor Quaglia, for this question. Yes, it is related to the workspace because the possibility to scan in this case the whole axle of the train car requires the possibility to span from one rail to the other one, and in order to keep also the low profile, so the teeny profile of the arm, we need to how to say, span from one side to another in a linear way. It is the more compact we found. And
okay,
I think
I understand.
okay.
I was supposing that this was the reason, but I want to have your comment about it.
Yeah.
Okay. I want
also, just to complete this question, to the answer, we test in the first phase of the development. We use a commercial robot that is a 6 degree of freedom. Mm-hmm. But of course, kinematically, it requires more space, and we cannot achieve the requirements of the space. So that's why we then, after the first trial, decide to use this kind of design that seems like a fish that is very light and can go behind under the train.
Okay, I thank you so much. I don't know if there are any questions. We miss one question from the chat for the presentation before. So if there are no more questions about this presentation, I can read the previous one that was made by Antonio related to the previous presentation. Could the overall frame size have an impact on large application?
Well, perhaps I may answer, because I guess that Eduardo just had to go away for personal problems. Definitely yes. In the specific application that Eduardo was mentioning, actually the frame is the biggest design. Well, the size of the frame is the biggest constraint on the stability of the control. The larger, the better in the specific application, but it cannot be as large as we wish. So yes, the answer is yes, and we have to cope with it. Normally, it is a constraint, it is a specification. It is not something that we can handle as freely as we would like.
Okay, thank you so much.
So perhaps we can move to the last presentation of the second session, the last presentation today. Last but not least, the paper will be ground vehicle navigation in unstructured environments through learning-based methods by Dario Vastella and Giovanni Muscato, and the presenter will be Dario Vastella, which is a co-organizer of the workshop as well. Dario, the stage is yours.
Yeah. Can you see my presentation? Okay.
Perfectly, please go on.
Okay, so good morning again. I'm Dario Guastella from the Robotic Systems Group of the University of Catania. And today I would like to show you some of our works on learning-based methods for the autonomous navigation of ground vehicles, in particular, so field robots in the context of unstructured environments. So in spite of their rather long history, so because ground vehicles, as we know, are one of the first type of autonomous platforms to have appeared in robotics research, UGVs are still not so ready for autonomous deployment in so-called unstructured environments. But what is meant actually by structured environments? According to the Springer Handbook of Robotics, which is actually a definition more related to to robotic manipulators, an unstructured environment is in general any environment which has not been previously modified in order to simplify the task of a robot. So, but what does it mean in the context of, how can we translate this definition in the context of autonomous ground vehicles? It essentially means the lacking, we have environments lacking helpful landmarks or viable, sorry for the change, the lacking of landmarks and clearly viable paths. But what's important, more important, is that this type of environments actually are can find a lot of applications ranging from search and rescue of disaster response to agricultural robotics up to planetary explorations. And as we can see, these are either crucial scenarios as well as very challenging. Learning-based methods can help us actually in providing some support in the perception of the environment. So to support the navigation in a context-aware mode. Here, by perception, we refer to the global block of inferring high-level data from the sensory data. We have, in general, two main approaches to deal with the autonomous navigation of ground vehicles in a unstructured environment. The first broad category is one based on the so-called terrain traversability analysis, and the other one are end-to-end methods. If we recall the well-known sense, plan, act pipeline, here we can see where TTA and end-to-end methods place. TTA essentially relates raw data to some outcome which can be used to plan an action. But we need a further step. So the plan has to be converted into actual motions. End-to-end methods try to provide a direct mapping from the raw input sensory data, either exteroceptive and proprioceptive data, and directly translate this information into actions. So as we could affirm that the TTA implies a further processing step, which can be seen as a limit, but somehow can help us during the debugging, let's say, so during the testing and the development of our autonomous algorithms. A further classification that we can do, talking about autonomous navigation in unstructured environments through learning-based methods, and in particular to TTA systems methods, is between regression methods, classification, and mixed regression and classification. As in the machine learning jargon, regression methods essentially aim at inferring and to derive traversal cost. So a value encoding the difficulty of the field robot in traversing a specific area. Classification methods, of course, aim at classify the environment into classes with some navigation relevant features. I don't know if you want to classify grass from rocks, from sands, and so on and so forth. But nowadays there are very common also kind of hybrids between methods, so between regression and classification, which is one of the works that we have done recently, and I will show in the next few slides, Whereas regarding this classification, we have recently published a review, which is the one reported at the bottom of the slide. So regarding our approach, we treat the traversability problem and pose the traversability problem as a kind of traversable horizon prediction. So we try to estimate, we divide essentially the incoming RGB image from the field robot into this set of 9 vertical bands, and try to regress the array, the vector of 9 values, which are nothing but the normalized values of this traversable horizon inside each band. And this is a kind of hybrid regression and classification methods, because we are actually performing, the problem is posed as a regression of an array of numerical values, but of course inside within each band it is actually nothing but a kind of binary classification between traversable and non-traversable areas. This work has been published in the last edition, actually the 2020 edition of IROS conference. We dealt with this problem by using a deep convolutional model composed of 2 main parts, of 2 main blocks. The backbone is nothing but the Deep Lab version 2 convolutional model, which is a well-known state-of-art convolutional model used for the semantic segmentation, which has been simplified for the real-time deployment on ground robots, so on the computing resources of our ground robots. And then we have the traversability prediction model, in which at the very end we have the fully connected layer projecting the features which have been previously reduced to 64 into the K predictions of our vector. In order to prevent risky situations, we had to modify the loss for the training used for the training of this model. So essentially, we prefer to avoid the model to learn over-optimistic prediction. So we prefer to have to penalize, let's say, those traversability estimation scores which are actually worse than the real one. Which are actually better than the real one, so would imply a risky situation for the vehicle. And as you can see, there is a considerable difference between the original, the classical mean square error approach for the loss of the training with respect to our solution with the safety preserving loss. Finally, in order to generalize from on-road to off-road scenario, we introduced a domain adaptations strategy. So essentially, we trained in an unsupervised manner the model, starting from the model trained only on on-road images. So we have annotated on-road images, and then we perform an unsupervised training on unlabeled images. And thanks to the domain adaptation, we are able to obtain appreciable results even in our target domain, which is in this case the off-road environment. So to do our experiments, we used a tracked vehicle equipped with an stereoscopic camera, which is the Z stereo camera by Stereolabs, and also motor encoders, of course, for wheel odometry, RTK differential GPS, and attitude heading and reference systems, as well as the HUD LiDAR. For the low-level control, we have an FPGA-based board, which is the National Instrument Single Board Rio. But most of the high-level functionalities are running on a Raspberry Pi 3 Model B+, along with the GPU NVIDIA Jetson TX1 for all the deep learning-based part. All of this software is running in ROS. So, we collected the data by running a 30-minute driving of our robot in real environments. So either in the on-road and the off-road scenarios. We collected 5,000 images, which are actually nothing but the frames of the video. But of course, in order to avoid the duplications, because during the navigation, very close frames would be actually too similar, we introduced a kind of thresholding methods strategy to essentially pick only the frames after some travel distance or after a specific amount of rotation in the heading of the vehicle, or a combination of the two motions. In this manner, we moved from the initial 5,000 images to only 922, which were actually pretty enough for the task at hand, as it is possible to see in this slide. As you can see, here we have some results that we obtained for our model. In this case, this is, of course, the raw input image. This is the prediction obtained only by training the model with labeled data on the off-road scenario. This will be the output of the model if we train the model on, but when we train the model on the on-road scenario. As you can see, the model has somehow learned some line-like features, but of course the prediction is not good because we are excluding this traversable area, which is the grass. Here, this is the results of the same model trained in a unsupervised manner on the off-road images with the domain adaptation, which is of course a little bit worse than the ideal case with the training on the off-road scenario, but it is of course better than the previous results without the domain adaptation. So in conclusion, we have proposed with our method an approach for introducing the safety preserving loss in this type of work, which is relevant in the case of unstructured environments, of course. And the learning-based method that we adopted has proved to be robust and able to generalize to several types of environments. As a future development, we are currently working on an alternative way, as we saw at the very beginning. So not only this kind of traversability-based approach, but another end-to-end approach based on reinforcement learning. Thank you very much for your attention.
Thank you very much for your presentation.
Thank you.
Is there a question in the audience? We have time for one.
Yes, there's a question from the audience here. I will have to repeat myself, but okay. No problem. Yes.
But in future, this training will be used to get the road and then plan on this road to navigation. I didn't get the final point of the training.
So the question is about the data collection. So the answer is yes, we do the data collection by manually calibrating the vehicle. Yes, actually, our final aim is only to work on the off-road scenario. So, but since we had some good results on the on-road, we start from that. And then we develop the domain adaptation solution. That's why there is this kind of weird, let's say, distribution of the dataset. But for instance, in the newer work we are currently working on, we are directly focusing the off-road scenario so we do not have any plan to work on the on-road scenario and to the automotive path planning, if this is your question. Or do you have any other curiosity?
That was my first part of my question. The last part is where this training model will be applied.
Okay. So you talk about applications now. Okay. We have currently a project on agriculture robotics. So that will be the very first application scenario where we plan to apply this model. You're very welcome.
Okay. Just let me add just a little thing about this. Since this is relevant for the research we are also doing here at the Polytechnic University of Bari. One thing you should also look at is trying to include the mechanical properties of the surface. Since you are now relying on aerostatic sensing, so you are building your traversability guess or assessment based on how you look at the data. So based on color, basically on color, since you are using images. But you can look, for example, at one sandy surface that is perfectly flat, but very soft. So you will assess this surface as very traversable, and the robot will actually shoot an hazard of the robot. Well, this is just like a future work, something to look at like in the future.
Yeah, of course, traversability can include also all this part of the terra mechanics prediction. So soil interaction, wheel-soil interaction. There are a lot of works on. There are several ways to face this problem, and that is actually probably the reason why I think that end-to-end methods, there are some of them also combining this kind of proprioceptive data. And since the interaction and the modeling of this type of interactions is not that easy at all, probably end-to-end methods can help to find a key to, or at least an alternative way to combine all these aspects at once.
Okay. So I think yeah, if you can. So I think we managed to close. If you can, please, Radio, can you close your microphone?
Yes.
Otherwise,
just a second.
Okay. So we managed to finish in time our workshop. So we are very happy with this, and especially because all the presentations were really very nice and good. So my congratulations to all the presenters for this wonderful workshop and job. And hopefully this is just like the first step of a long road that we can walk together. So the first episode of a very long series, let's say. And so I'm very happy with this event. And I don't know if Giuseppe and Marco have more to say. And let me just thank again all the speakers.
Okay. I kindly ask to the people who are now connected if they want to switch on the video, so we can have a picture on it, and maybe we will share it after. And finally, I want to thank you all for the interesting workshop. I'm sure that in the future we will have other opportunities to work in a RIM context in order to show the results. And really, it was a nice experience for us. Marco, do you want to add something?
You said everything that deserved to be said. I can just add my own thank you to everyone, to the speakers, to the audience, and for you to organizing this very exciting workshop. And see you next year.
Okay. Maybe we can take these pictures. If everyone turn the camera on, we can try to have like
There is one missing more. Okay, I take it. Okay, I will share it.
Okay, so thanks again to everyone, and enjoy your lunch, and see you soon then.
Thank you.
Bye-bye.
Bye.
Thank you. Bye-bye.
Bye.
Bye. Thank you to everyone.